This lesson we're going to discuss counter circuits, and counters are used in digital circuits to generate a count or a binary count, usually very logical, 0, 1, 2, 3, 4, 5, 6, 7 in binary. And we can do decade counters which only go from 0 to 9. We can do full 4-bit 0 to 6, 0 to 15 counters. You can do any kind of counters you really want. We can even reset them in the middle. We can also use counters to set up output frequencies based on what the input frequency is. So we can split frequencies in half. We can split them into sixth. We can do divide by 10. Do all kinds of different stuff with counters. So let's take a look at how counters are set up and what they look like, and we'll do some output waveforms for them. So here's just a basic counter circuit, and this one is using JK flip-flops, which almost all counters do because we take advantage of the toggle function of the counter. And you'll see that we have the clock going into one of our JKs, and it only goes into one. This particular counter is called a ripple counter. Okay, so if you remember, ripple is kind of like drop a rock in a pond that ripples out. In other words, the rock didn't make water over here move. It was the ripple affected the next ripple, which affected the next ripple. So the same thing applies to these counters. One clock affects all of them indirectly. Cascading counters is another name for it. Asynchronous counters, in other words, they're not synchronized to a single clock. That's another name for it. But ripple counter is probably the most common name for these that you'll see. You'll see that J and K are both at high in all of these. So that means we're in toggle mode. If you remember toggle mode, it's just going to inverse state whenever it receives a clock pulse of some kind. The clocks are negative edge triggered. Right? They have a mouth and a bubble, so they're negative edge triggered. We have all our presets tied high, so those aren't going to do anything. We're going to give it a reset pulse at the very beginning just to kind of get an initial situation to where we can start counting something from somewhere. In this case, we're going to reset them all to 0. And we have the output of Q goes into the next clock, but we also are drawing the output of Q. So our waveforms right here for Q0, 1, 2, and 3 are coming from the outputs of those Q outputs. So you can kind of see where they're coming from. So for these clock circuits, what we're going to do first is we're going to figure out, and I also got 80K going in a clock pulse. The first thing we're going to do is we're going to figure out what our startup condition is. Where we're going to put a reset pulse right here. And a reset pulse on clear is going to make, remember, anytime you reset or clear a flip-flop, Q goes low. So these are all going to start low. And I'm only going to go so far over. I'm not going to go all the way. There we go. Okay, so they're all going to start at low. And we're going to look at next is we're going to look at, since they're all negative edges, we're going to draw dotted lines or highlight your lines on all your negative edges. So I'm going to draw that down on the negative edge, this down on a negative edge. And again, if you don't have a highlighter, you want to use a pen or a pencil, you can just do a dotted line down here. I've done that for ages. Highlight. It's a lot of pulses here, and actually we won't even see all the changes. We should have had we could have had room for maybe 17 or 18 pulses. We would have seen all the changes go back from one number to the other, but since we don't, we'll go with what we have here. Okay, so these are going to stay low over to the next negative edge. At that negative edge, then there we'll do something. So what we can do for the first one is we can just say, okay, every negative edge of this clock, every time we see a negative edge, we're going to clock or we're going to toggle this flip-flop. So every negative edge, we're just going to flip state. So it goes high, goes low, goes high, goes low. And again, we're just toggling every time. Okay, so just started low, toggle high, toggle low, toggle high, toggle low, on and on, all the way across. So we kind of ignored all the rest of these and we just looked at that one flip-flop. Now let's look at the next flip-flop. Where is the clock for this one coming from? Well, the clock for this one is coming from Q0. So Q0 is now our clock for the Q1 output. So for every negative edge of this one above it, we're going to toggle. So you notice it's not on every dotted line, it's just on every other dotted line. So it's every negative edge of the one above it. Just like that. Now this one's doing the negative edge of Q1. So we're going to stay over here all the way over to the negative edge of Q1. Just like that. And then this one, Q3, is the negative edge of Q2. So you can see we're really only going to change once right there and going over. Okay, so this one is doing the negative edge of the clock. This one's doing the negative edge of Q0. Q2 is the negative edge of Q1, and Q3 is the negative edge of Q2. So if you wanted to, you could have just done your dotted lines just for the first one, and then do a dotted line for Q1 just on the negative edges of that one, and this one would have been just the negative edges of this one, and this one would have just been the negative edges of that one. So you didn't have to do all your dotted lines. I could have saved us some time by just doing just the top one. Now the mod number for these, and this little formula only works for ones that do not have an automatic reset, which we'll see in just a little bit what an automatic reset looks like. But the mod number only works for ones that do not have an automatic reset. And it's 2 to the n power, where n is the number of flip-flops. Okay, so in this case it's 2 to the 4th, which is 16. So our mod number is 16. Our divide by number is always the same as the mod number. So in this case it's also 16. There's a couple other things we need to look at. We need to look at which one's the least significant bit and which one's the most significant bit. Well, if you think about it, if you're counting in binary, and let's just do a 2-bit one. Which one changed the most often? Well, we know this is the least significant bit. That one changed every time, didn't it? And this most significant bit changed the least often. So the least significant bit changed every time. Well, which one of our outputs here changed every time we had a clock pulse, basically? That'd be Q0. So we know that this is our least significant, and this is our most significant bit. Well, if that's the case, we can go straight up here and we say, okay, this is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 1. That's probably enough. Do 4 of them. That's probably good. So this is a 0 in binary. 0, 0, 0, 1 is a 1 in binary. 0, 0, 1, 0 is a 2. And 0, 0, 1, 1 is a 3. So is this one counting up or is it counting down? Sure looks like it's counting up to me. It's getting higher for each one. And you'll see it goes, well, there 1, 2, 3. Next one will be 4, 5, 6, all the way up till we got to 15. So this one's a count up counter. Another thing to note about these is the frequency actually gets split in half for each one of your outputs, as long as you're not doing any kind of resetting somewhere in the middle with an automatic reset. So we can say this 80K gets divided in half, it's now 40K. 40K gets divided in half, now it's 20K. 20K divided in half is now 10K, and this last output is 5K. So one of the neat things we can do with this divide by number is if you take your original frequency of 80K and divide that by our divide by number, which is 16, we will get the 5K output. So it's a really neat way of double checking that your frequencies are correct. So this one, depending on where we took our output, we could use this as a frequency divider. If we have an 80K signal in, let's say we needed a 20K clock signal or a pulse, we could pull out of Q1 and tie that to something. It would pulse every 20,000 times a second. So it's a neat way to divide your frequency up. Okay, let's look at the next one. And if you need to look at this one a little bit longer, just pause it. But we're going to go on to the next one. This is another counter. And you'll see the only difference between this one and the last one is instead of coming from the Q going to Q0 and the clock, we're coming from a Q naught and going to the clock. Okay, so Q naught to the clock. And the Q naughts are also the ones that we're drawing. So Q0, 1, 2, and 3 are being drawn from Q naught. So the first thing we need to do is figure out, and the negative edge triggered again. So we got this reset pulse. Well, reset on a flip-flop, remember, anytime you reset a flip-flop, if Q starts low, Q naught has to start high anytime you reset a flip-flop. So reset a flip-flop, Q goes low, Q naught is going to be high. So all of our outputs are going to start high. Okay, so Q goes low, Q naught is high. Negative edge triggered, so let's do our highlighter again, and I'll only do the top one this time so we won't have to do so much drawing. So it's just the top one, since that's all we really need for these clock pulses anyway. Okay, so we're going to go over to that first negative edge, and what's going to happen? Well, the first, ignore the rest of them, just look at this first one. What happens with every clock pulse? Well, we're in toggle mode again, so in every negative edge we're just going to toggle the flip-flop. So it goes from high to low, high to low, to high to low. It's just going to do that all the way across. So the first one we didn't do anything weird or strange to. The next one is doing the negative edge of Q0. So let's do our highlighter again, but let's only do the negative edges of this one. So there's a negative edge, there's a negative edge, negative, 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 negative. So we're going to be high over to there, and again, toggle mode is just going to toggle every time we see a negative edge. Yeah, flip states every time you see a dotted line, basically. Now, our highlighter again. This one now is seeing the negative edge of Q1. So every negative edge of Q1, we're going to put a line or highlight, and we're going to toggle every time we see that negative edge. So it goes low, goes high, goes low, and one more negative edge. So we got a negative edge there, actually have a negative edge there, so we actually got two of those. So it's positive over to there, we go low all the way over to there, and it toggles high. Okay, so our mod, again, we didn't do any resetting, so it's 2 to the 4th, which is 16. Divide by number is also 16. And up and down. Well, since we did Q naught, you would think it'd probably count down now instead of going up. But let's see. We changed every time on this, so it's still our least significant bit. And I'll give you a hint. Q0 is almost always your least significant bit. This is your most significant bit. So it goes from 1, 1, 1, 1 to 0, 0, 0, 0, 0, 0, 0, 1. 0, 0, 1, 0, and that's probably enough to do 4. So this first one was all 1, so that's a 15. And we went to 0, and we went 1, and we went 2. Well, it looks like it's counting up. Right at the beginning, it looks like it was almost going to, think about it, almost looks weird. They're going 15 to 0, but then it starts counting up. So it is an up counter. And it's just like if you were to count from 0 to 9, 0 to 9, 0 to 9, 0 to 9. Once you reach 9, it would roll over back to 0. So that's what this is doing. It's hitting its highest number and then rolling back over to the lowest number. So it's still going higher. Frequency wise, we're still splitting in half here, so the frequencies are going to be split up. And then you can do your final output frequency by doing your 150 divided by 16 and get your final output frequency. So that still works too. So it divides in half each time. So you'd have like 75K and on and on and on. Okay, let's go on to the next one, and the next one will be a little strange looking. This one looks a little weird because if you look at your outputs here, well, we've still got negative edge, we still only have one clock, so we still know it's a ripple counter. But what we've got going on here is we've got Q being the one we draw, but we're clocking on Q0. So do you see that? You're drawing Q0 right? You're drawing off Q, but you're clocking off of Q naught. So we draw one, clock off the opposite of it. So what we see down here is going to be the opposite of what's actually feeding the clock of the next one. So let's go through and figure out how this is going to work. Again, for the very first one, ignore all this other one. Don't even pay attention to it. What's going to happen with the first one? First of all, when we reset all these, Q, which is what we're drawing, goes low, right? We reset. So Q goes low. We can go ahead and draw the lows for all these. Okay. And this very first one, every time we get a negative edge of this clock, that is going to toggle. So there's really nothing magical going on there, nothing strange or weird. So it's every negative edge of this very first one will toggle. Okay, so it's draw our negative edges and just sit here and toggle all the way across. And that's going to set up our clock for our next one. Okay. Now, let's look at what's going on for Q1. Q1 output is coming off of Q, that's fine, but it's getting clocked from, it's not getting clocked from Q0, it's actually getting clocked from the opposite of Q0. So we're still getting clocked on the negative edge. In other words, we would still toggle when it receives this signal. But since we're drawing the opposite of that, it's going to look like it's a positive edge. So think about that, look at it again. We're really truly clocking off the negative edge of this Q naught output. So it is still negative edge. But what we actually see down here at the bottom is going to be the opposite of that. It's going to look like it's positive edges. So instead of putting our highlights on the negative edges now, we're going to put our highlights on these positive. Oops, sorry about that. Let's erase that. We're going to put them on the positive edges, not the negative edges. So there's a positive edge, positive, positive, positive. Okay, just because we're drawing the opposite of what we're actually clocking on, we'll see the opposite clock. So now we're just going to toggle every time we see a positive edge. Just like that. The next one, again, we're clocking off this line, but we're actually drawing this one, so it looks like the opposite, right? Negative edge, it looks like a positive edge. So it's going to be positive edge, positive edge, positive edge. So it's going to toggle every time we see a positive edge. All the way over to there, and all the way over till we get to the end. And the last one, the same thing. It's clocking off the negative, but it looks like it's a positive, so positive edges. Okay, it's like that. The mod number, believe it or not, I still haven't changed it. It's still 16 because it's still 2 to the 4th. I haven't done any kind of automatic reset. Divide by 16 still. Up, down, let's figure that out. Well, this is still our least significant bit. This is still our most significant bit because that one changes the most often, so it's the least. So we've got 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, and 1, 1, 0, 1. So here we have a 0. Now we've got a 15, 14, 13. Well, now what does it look like it's doing? Well, it sure looks like it's counting down to me. It's going lower as we go across. So this is how you make a down counter out of negative edge triggered flip-flops, is you do it by doing the inverse of them. Frequency, still going to divide by 2, so we've got a 20K, 10K, 5K, and 2.5K. So you're still dividing in half each time. And again, if we take that 40K divided by the 16, you're going to get that 2.5K. That's our final output frequency. It's pretty neat how it works. Okay, one more of this type of flip-flop, or this type of counter, And this one, you'll notice we're going from, the clock is still negative edge, but this time we're drawing from the Q naught. We're clocking off of Q, but we're drawing Q naught. So reset condition for these, anytime you reset flip-flop, Q goes low, so Q naught has to go high. So we're going to start high on all these. And then first one is just going to be negative edge, nothing weird going on there, so it's negative edge. Every negative edge we're going to toggle. And again, highlight it or dotted lines, whatever you want to do. It's nice to have something kind of indicating where to change it, because you kind of lose your place if you don't. So we toggle on each one of these negative edges going across here. Okay. Now we'll look at this thing again, and again, this is really going to clock off the negative edge, but since we're drawing on the opposite, it's going to appear that it's a positive edge. So just like the last one, it's going to look like it's a positive edge. So it's a positive, 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 positive edge. Up in, and we're going to toggle on every positive edge. And same thing for the next one. It's going to be positive edges again, since it's clocking off the opposite. And the last one, again, positive edge. I only have one of them. So if I can draw a straight line all the way over here. Yeah. And then that one goes low, and it stays that way all the way across. All right. Again, least significant, most. This one's going to be 1 1 1 1, 1 1 1 0, 1 1 0 1, 1 1 0 0. And what is that? That's 15, 14, 13, and 12. Okay, because remember you got 1, 2, 4, 8. Add those up and it gives you those numbers. So it sure looks like we're a down counter. Mod number and divide by number still is the same since we didn't change anything. And the frequency is still going to divide by 2. Okay, so we got 80, 80K, 40K, 20K, and 10K. So you take 160K divided by 16, and it equals 10K. Alright, so it should pretty much show you every possibility combination of all these, just kind of get the waveforms. These are the only ones we'll do waveforms for, is these asynchronous or ripple counters. We won't do waveforms for the synchronous ones, but let's take a look at the synchronous ones now. The synchronous counters, you'll notice, are kind of similar in that they use JK flip-flops, but there the similarity pretty much ends. We do have a clock, but the clock now is tied. If you notice, they're all tied to the clock. Every one of these are tied to the clock. That's why they're called a synchronous counter. They're synchronized to one single clock. The deal why you'd want to use these is, for these, they're going to change every time. In other words, every one of them are either going to toggle or not toggle at the exact same negative edge of the clock. Whereas the asynchronous ones, what happens is, if you get a clock pulse that looks like this, and let's say they're all negative edges here, well, what happens is, remember, we have a propagation delay, and propagation delay is actually going to push that a little delay here between there and there, and it may only be 20 nanoseconds or so for the first each one of them, but by the time you get 16-bit counters or 32-bit counters, 100 times that is, you're getting into milliseconds now, and there's would be quite a delay between one changing and the other. So they don't use the synchronous counter or asynchronous counters for large bit count counters. They're usually used for 4-bit or 8-bit counters, and that's pretty much as high as you ever see in an asynchronous counter. Synchronous counters, though, you don't run into this propagation delay problem because they're all changing at the same time. So this one will get clocked at the exact same time as that one. So they all change at the same time. There's no delay. For this one, the biggest deal is you got these AND gates too that also tell it when to toggle. And if you want to, you can read through the book and it goes through the step-by-step on how to calculate that. It's not hard. It's just more than I wanted to go through here. I want to really just show you these automatic resets with these synchronous counters. The waveforms look exactly the same as what the asynchronous ones look like that we did before. So that's why I'm not going to go through more waveforms for you. What I want to show you here though is, first of all, we have a counter that is going to start at a number and count up, and then it's going to automatically reset at a number and go back to that original count. So what I need to, the first thing you want to look at is what count does this counter reset. So we have to figure out, okay, where does it reset at? Well, the best way to do this AND gate, or the NAND gate right here, when it has anything but two highs, let's say it has a 0, 1 on it. Well, a 0, 1 is going to give you a 1 out. A 1 is not going to clear these active low outputs, right? So it's going to operate normally. But as it's counting up, at some point in time, we're going to get two highs. When you get two highs there, this one goes to a low, which instantly resets these flip-flops, right? So you got lows on all these, and it's going to say, okay, I need to reset or clear these flip-flops and start all over again. So when are we getting these two highs? That's what we need to figure out. So the easiest way to do this is to number your Q0, 1, 2, and 3 as binary. 1, 2, 4, and 8. Okay, so you got 1 for Q0 because that's our least significant. Q3 is 8, the most significant bit. So 1, 2, 4, and 8. And then you look and see which ones these are attached to. So it's attached to a 2 and to a 4. Add those up, and it equals a 6. So on which count does it reset? It resets on the number 6. Now what's interesting about this though is the instant it hits 6, it actually will not do 6. You won't actually see 6. If I were to write these in decimal, it's going to start at 0, 1, 2, 3, 4, 5, and it's going to hit 6 just for a brief moment. I mean, you're talking nanoseconds. It's going to see a 6, then it'll go back to 0. 1, 2, 3, 4, 5. 0, 1, and on and on and on. Well, mod number, to figure out what the mod number is how many distinct counts you have here. So we've got from here to here are the number of unique counts. In other words, you got these are the same thing as these. So how many of these do you have? Well, you have 1, 2, 3, 4, 5, 6. You have 6 distinct counts, so it's a mod 6. What's also interesting is, let's say you have a clock frequency of a 60 hertz signal. If you divide 60 by 6, you get a 10 hertz signal, right? So that very last output, which this one will actually always stay low, but the Q4 or the Q2 output will be at a 10 hertz signal. So that's another use for that divide by number. All of my synchronous counters will be count up counters. I'm not going to mess with you and give you count downs and stuff. They'll all be count ups. Okay, so I'm gonna ask you what number it resets on. What's the mod number or divide by number for the flip flop, and you get, or the counter, you get that from the number of distinct counts you had. What if I started at what if I counted from 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. What if I had a counter that did that and it started at 2 and only went to 6? Well, you would go from there to there. How many distinct counts does it have? Well, 1, 2, 3, 4, 5. So this would be a mod 5. Okay. So let's look at another example. And again, this is the same thing as we had last time. So do your 1, 2, 4, and 8. And this one's tied to 1. And this one's tied to 8. That equals 9. So it's a 9. It actually counts from 0 to 8. In other words, 8's the highest number we'll actually see. So 0 to 8, if you count those out, it actually is 9 different numbers. And again, they're all count ups. So just add these two numbers together, 1 and 8, and you got it. Now, for example, what would happen if I had maybe this one tied down here as well, maybe a 3 input? Well, then we would have 1 plus 4 plus 8 That would be a mod 13. So it would be 13. 13 because it'd go from 0 to 12. It would still be a count up. So you can have multiple inputs on these too. This one adds something else to the circuit, and I actually tied this. Should be down there. I forgot to fix that in my slide, but this should tie down here for it to work properly. So what this does is it adds what's called an automatic reset, or a manual reset. So this is a manual reset. It allows you to be able to push the button and tell it to go to a reset condition right there. In other words, go to 0. Now start counting up. And then if you want to stop in the middle, you can hit it again and it'll reset. So it's a good way to get it to go back to the start position whenever you want it to, because maybe you want to stop it at 5, and sometimes you don't want to have to wait around for it to go all the way around. So you can hit that button, it'll start back up. So this works exactly the same as the other ones. The only thing I've added to it is this NOR gate, and the NAND gate became an AND gate. And this one, normal operation is this thing's going to be sitting here at ground. It's going to be sitting here at 0, and this is probably going to be sitting here with a 0, 1, 0, 0, whatever. So that's going to be a 0. 2 lows into an OR gate gives you a high. A high on all these clears does nothing at all. If I push this button right here, it shorts it out to high, so it makes this go high. This will now go to a low, which makes it reset all the flip-flops. So it goes back to, in this case, it starts at 0. If I were to leave the switch open and this hits 2 highs, that high now becomes a low and resets. So it also has an automatic reset. So you got a manual and an automatic. You figure out the reset number by the same method we used last time. 1, 2, 4, and 8. And we have 4 plus 8 equals 12. So we've got 12 for reset. The counter actually goes from 0 to 11, so that's still a mod 12. And we still count up, so we didn't change anything there. And just to give you another example, what if I did not have this line right here? I had both of these shorted together going up to Q2. Well, remember it's 1, 2, 4, and 8. Well, if they're both going to 4, it's still just going to be a 4. In other words, when that goes high, you got a high out and you got a reset. So you got a 4 at 0 to 3, so that's a mod 4, and it still counts up.